accepted.
Fantastic. Welcome, everyone. I'm really excited to be here. It's been many years since I've been back to Krakow, and I just love the city, so I'm so happy to be back. What I wanted to talk about today was testing software architecture, which is kind of an interesting concept when we think about it, actually. As a matter of fact, why is this topic so important? Well, this is why. You see, what you see on the screen here is just a small country road. It's a small bridge over a river. And think of that bridge as kind of the structure, the architecture, kind of holding up your system. And the cars across there are all the requests going through your system. Well, this looks like this bridge works for that much traffic. But what happens? Like our systems, towns grow. And they continue to grow into something that looks like this. Now all of a sudden there's that same bridge that was constructed many years ago with a lot more traffic, a lot more requests going through. And if we don't pay attention to the structural aspect of that bridge, this is what will happen. That's why this topic is so important. Because too many times, our systems simply crumble and fall apart. That's what we're going to look at in this session. How to test software architecture. Now, I like to use examples to take an abstract concept and really make it more concrete. So imagine, if you will, this kind of system. Now, this is a student test-taking system, standardized tests throughout the country. Students who are assigned to various classes go to these testing centers or their school and take a test. It's a timed test. And if we look at this kind of system, we look at the overall flow of what happens. We have a student, or well, there could be up to 120,000 students. They sign into the system. Then they get presented with their first question. The students answer that question, and once they answer it, they then get presented the next question. Well, about at that same time, the answer is auto-graded, and those results stored in a database. So when we look at this kind of system, how do we test it? Well, one of the ways is to write unit test cases. And here's an example in Python. As a matter of fact, here is a test for that student sign-on to make sure it works okay. As a matter of fact, let's do that. Let's make sure we run the test here. Okay. And do a little prayer to the demo gods. Execute the test. And it worked. Fantastic. Okay, so that's what we do every day. We write unit test cases or scenario test cases, execute them against the functionality, and it works. This system is ready to go. We're well practiced in this kind of mode of testing. Well, let's take a look at the overall architecture for this system, because it consists of 6 services. So notice up here we have an admin user interface, and this is for the administrative staff with a corresponding gateway. We've got a reporting service that generates all sorts of student reports, teacher reports, school reports. We've also got a test maintenance service. This is for creating the tests, modifying them, scheduling them, and generating a roster. Over here is the admin sign-on. It allows for security and admin staff to be able to sign into the system. But over on this side, we've got the whole testing area. We've got a student user interface with a testing gateway, the ability for students to sign in based on that roster of what class they're in and what school they're in, the main part of the system, which is the test taker. This is the service that essentially delivers a question to a student, receives the answer, and sends it to a queue. And then finally, the auto-grader, which receives those. All right. And then grades them and persists those answers. Okay. Well, here's a question for all of you. How do I test the architecture? We just went through a unit test case to make sure that the sign-on service works. But shouldn't we also test the architecture as well? That bridge that's holding up all of those cars? We probably should. What does that even mean? Well, when we test a software architecture, essentially what we're looking for are areas of structural decay, cracks or seams in those big concrete pylons holding up those highway bridges or bridges over water. That's what we're going to look at. Now, in this session, I'm going to show you how to identify and find and locate those cracks in the pylon and see how many cracks we have in our particular systems. When we go to test a software architecture, not the functionality, but the architecture itself, there's two ways we can do this. The first is through operational characteristics. Those things like, does it scale? Does it perform okay? Are there errors? What is our error rate? But then there's also tests that we're going to write in this session that have to do with the structural integrity of that architecture. These two tests answer three primary questions. And the first one is this: are changes that we're constantly making to the system impacting the architecture? Is the architecture still sound? Are changes to the environment impacting the architecture? Maybe it's an upgrade to our networks, an upgrade to a platform. Maybe it's a replatforming. Is that impacting the architecture at all? And number three, can you actually verify and demonstrate the structural integrity of your architecture? That structure that's holding up all of your source code. Can you say it's structurally sound? Can you demonstrate that, in fact, this system will scale to 120,000 students and still maintain the response time that we need, because this is a timed test? That's what we're going to look at. Okay, let's take a look at the operational characteristics first. Those tests that we can write to verify the integrity of our architecture from an operational characteristics standpoint. These are just a partial list of what I'm talking about. Is the system available? Is it reliable? Does it perform? Is it responsive? Is it fault tolerant? What's our error rates? All of these are operational things that we can actually measure. Now, here's a very interesting one. We have to ensure that the system is reliable. Is your system reliable? Why? Yes, of course it is. How do you know? How do we define reliability? If we're supposed to be creating highly reliable systems, how do we define that? If you think about it for a little bit, we all know what reliability means. But how am I going to demonstrate it to you? That's a good question. I know. Is the system available when I need it? When we're actually executing tests, and we're having testing sessions with students, is the system available and up and running? Because if it's not very reliable, is it? I know another one. Watch this. I go to take a test, and the answer for that question is B. And all of a sudden, I get it marked wrong because the system didn't recognize that I marked it B, but thought it was C. The data is not very reliable. So data integrity is another aspect of reliability. Ooh, how about this one? Type, enter. It just kind of froze. Come on, this is a timed test. I need the next question. Ah, there it is. And now answer another one. Instant. Answer another one. Wait. You see, so that's like the responsiveness. Is that reliable? Is it consistent? What about error rates? The number of errors that I generate. These are all really good signs to measure a reliable system, isn't it? So you know what we just did in that last minute? We just defined reliability. And here, by the way, is the secret. Are you ready? If you can measure it, then you can define it. That's the way to define what these things mean. How would you measure it? What would you measure? And now we can define these. All right, so how do we write tests for these? Those tests are called fitness functions. And a fitness function was first coined in the book Building Evolutionary Architectures by Neil Ford, Rebecca Parsons, and Patrick Qua. An architectural fitness function is some sort of objective integrity assessment of some sort of architecture characteristic, a way of being able to measure all of these operational characteristics. Now, not surprisingly, a lot of you are currently running fitness functions. A lot of the tools that we use for observability, even Kubernetes, Prometheus, Datadog, SonarGraph, these are all tools that are running in our ecosystem that help us identify problems. They're good. But what we're going to see in this session is that those tools fall short of some of the tests that we need to actually write to verify that our architecture is sound, that that bridge is not going to collapse. So I like using these kind of tools to extract those kind of metrics. But let me show you another way of writing fitness functions. This is the way I usually write them. Now, if I can, I extract all the metrics from all of these observability tools, metrics tools. But also, it doesn't need to be that complex. So let's say we have a system, a website, a service, whatever. We can stream various metrics out to, for example, Kafka or an asynchronous queue, all sorts of things, response times, uptimes, the number of requests I have, error rates, all of these things, any kind of information I can stream. Then I write a capture service, and this is all in production, to be able to capture that raw data, possibly filter it, and store all those raw metrics. Now comes the fun part. Now we write an analytics service. This is really our fitness function. We start measuring either thresholds or trends that are happening in our system. And then if I reach a certain threshold or I reach a certain trend, then in that case, I then notify somebody. All this is running behind the scenes in production, and I don't even know it's happening. So this is what we're going to be writing, are those analytics services, the tests that are executing to really test our software architecture. Now, there's two kinds of tests that we can actually write. We could write trend-based tests that are kind of measuring things over time. And basically, if I start noticing an upward or downward trend, notify me. But I can also write threshold tests as well. If our response time exceeds 900 milliseconds, notify me. In general, Each of these have their own purposes, but I really prefer trend-based tests because, yes, I already know a server went down. You don't have to notify me. And we get too many false positives with the threshold-based, whereas trend-based ignores those and says, yeah, we had a little hiccup, but overall, things are good. And so most of what we're going to write in here are the trend-based measurements. Now, before we write some tests, we need to answer one question. When should I test an architecture? Because there's two ways I could test. I could use a triggered fitness function, which is a function we're going to write that basically is triggered in your CI/CD pipeline. Or they could be continuous fitness functions. Whoops, went one too far, hold on. They could be continuous fitness functions, which basically are the ones I just described, just running always in production. Well, which one's better? When should we do the tests? Well, let's actually analyze these. Because let's take a look at triggered fitness functions, those that are running triggered upon a release or a build. Well, the clear advantage of these kind of tests is that we find out that there's an issue before we release that software. And that's a really good thing. Of course, we don't want to release and go, oh dear, it's not scaling anymore. Yeah, so these make sense. But we have to maintain those tests. Who wants to maintain all of the hundreds of those kind of tests that are triggered? Not me. Nope. But it's worse than that. We also have to maintain the data as well. And this actually becomes even harder. But it actually gets worse than that. Because what we're really trying to do with a triggered fitness function is simulate user behavior. And that's really hard to do. So what happens is we end up generating some hotspots in the database because we're clustering information together. So something that necessarily maybe goes from a row-level lock to a table-level lock or a page-level lock, and all of a sudden now, the system just freezes. Whoops, we did something wrong. No, the system's perfectly fine. It's our tests that are the problem. Oh, these are essentially what are called synthetic transactions. You know, it's kind of interesting. We all think we know what the users do in our system. Well, I have been in this industry for 37 years. And let me tell you, we have no idea what users are doing with our systems. Yet we're trying to simulate that behavior. Do some of you remember Power Builder? Remember that back in the day? Yeah, boy, that was fun stuff. I did a lot of coding in Power Builder. As a matter of fact, many years ago in the mid-90s, I was involved in writing a call center application that was written in Power Builder. Well, it was deployed as a desktop application, of course, and we had one particular user at the call center whose system kept crashing. We could not figure out why. It was only one single user. We went through logs, we could not figure this thing out. So we did the smart thing. Myself and another colleague shadowed this call center rep. We went to the call center, stood there, and watched her work. That's the right thing to do. So she's taking calls, yep, and we're like, this system's working perfect. Until one particular call. Yep, so I'll need your credit card. Okay, I understand. Yep, I'll wait a little bit while you find it. And so the call center rep got bored. And what did she do? She took her mouse and just started just moving it all around the screen. Kept moving it all around the screen. All around the screen. Suddenly, it froze. Bingo! We had actual code inside the mouse move event within Power Builder, which kept triggering and triggering and triggering and running out of memory. Who in the world would think of that test case? That's why this doesn't work well. All right, well, let's take a look at continuous fitness functions, those that run in the background. They're just continuously running when we write the test. Well, the first thing we notice is the fact that we don't have to maintain any tests. This is all analytics based on gathering information and data. We don't have any test data to maintain. As a matter of fact, we are getting actual test volumes of real usage of that data, actual user behavior. We don't have to try to guess what's happening. Well, that's a huge advantage because now we don't have to spend time and effort and money to write and maintain these tests. And it's much more accurate. But guess what? We can measure trends rather than snapshots, which is a good thing. However, we don't find out we have a problem until we're well into production. Isn't it interesting? Those are the trade-offs between these two. With triggered, we get early detection of issues, but it's much more costly and less accurate. With continuous fitness functions, these tests we write in production, well, those are a lot cheaper, a lot less effort, and much more accurate, but later detection. Which one is more important to you? This, by the way, is why we can't have nice things. Trade-offs. All right, well, let's go back and let's actually write some fitness functions. So let's go back to our student test taking. Here's some of the requirements. What do we test? Well, if we tease out what's important in this system, we see that it is a timed test. It's got to be available. It's got to be responsive. It's got to be reliable, recoverable. We notice that we have to go up to 120,000 students. Well, that's all about elasticity because the system isn't used all the time. But then all of a sudden, boom, 120,000 students. Also, high data integrity needs. We cannot ever, ever, ever lose a student answer. And also security concerns. We don't want these tests stolen out of the database. We don't want students taking a test for somebody else. These are our concerns. This is what we can test. So, here's the main processing flow. Student basically answers a question. The test taker receives that, sends it to a queue, sends up the other answer. The auto grader dequeues it and marks it, either correct or incorrect. And then finally, persists it in the database. Okay. How can we guarantee no data loss? That is one of our main objectives. You cannot lose ever a student answer. So what can we do? Let's write a test for that. Well, any ideas? Let's see. How about a checksum? That would work. So I can actually record the number of student answers that the test taker received. I have that information. I could stream that information as a metric out to Kafka or a queue. Let's see. I can also know how many answers the autograder got, and I can stream that out. I can also query the database. How many answers were there for that testing session? But you see the problem here. Those numbers will rarely be the same. When will they be the same? When testing ends for the day. So this is where some of the tools that we use start to fail because now there's some logic that I need to add to this test. So basically, I can write a fitness function that says, oh, by the way, are there any students signed in? That's something else that I can query or stream. That's information I can gather. Yes, there's no students signed in at this point. Okay. Is there any information in the queues? Nope, the queues are empty and autograder is idle. Then I compare those answers. I write this fitness function And this is just continuously running in production, guaranteeing and demonstrating that all three of those points have the exact same answer all the time. Oops. We lost some data. That's the importance of these tests. It's not only to demonstrate that we're doing okay, but also demonstrating we have a problem. Why did that occur? Everything was running fine. Was it a change that we made in the system? Was it a change in the environment? That's what we now investigate. Let's talk about the elasticity. How do you test elasticity? Well, how do you define elasticity? I know. As the number of students increase, the response time stays the same. That demonstrates an elastic system. Because think about it. If we don't have capacity in our virtual machines, or we don't have enough threads, or we don't have enough connections to the database, what's going to happen? We're going to get connection waits or failures. And it's going to impact the responsiveness. So, what I can do is capture those metrics. I can actually capture what is the responsiveness, response times and timestamp, and user load within a sign-in, and also the test taker. We write that test, it's in that analytics service that's just sitting there running in production, and it's continually analyzing this. And if we write this, this is what we notice. Over time, there's some peaks and there's some valleys, but notice our user load is increasing, but our response time is pretty much accurate, is pretty much level. That is a very simple kind of mathematics. It looks like most of the data points are within 1 to 2 standard deviations from the mean. Yeah, that's a pretty straight line as opposed to a line that's going up or heading down. But notice what I've circled here. Looks like we had a little problem, didn't we? Response time started to go up as we started to increase our user load. But then it goes down. This is why I like trend-based, because we can explain that little hiccup by the fact that we had additional load, and as a matter of fact, those were instances that were starting. And once all those instances started, notice the response time improved dramatically. It goes up and down. That's an elastic system. Hey, but there's another function of elasticity that we could write a test for, to test our architecture. And that is the mean time to start of that test taker. Because did you notice, if I go backwards one, did you notice right here, backwards one, yeah, there we go. Did you notice, the longer it takes our test taker to start up, we're going to hit that red line, and things are going to start timing out. So wouldn't that be a good thing to measure? The mean time to start of our test taker? Sure, and that's actually information I can get from a service orchestrator, like Kubernetes, for example, or just have the service stream it out. Again, we don't need tools to do this. So I can measure the amount of time it takes before it's fully operational, stream that out, and write a fitness function. And we do. And we see that it's pretty consistent, whoops, until it's not. What happened? Oh, that was a new release of our software, everybody. Somebody made changes to that test taker, which effectively doubled the mean time to start. That is going to impact the responsiveness. I get notified, we fix it, redeploy, and now we're back down to normal. And that's the idea of these fitness functions. There's one more that we could write about elasticity before we look at structure. And that is, what about those queues? Because all we've been focusing on is this test taker, is sending all these answers out to the queue. But what if the auto-grader is too slow? And it can't keep up. those queues are going to fill up, and boom, the bridge collapses. So I could actually just continually query the queue depth of every one of those queues and write a fitness function to constantly monitor and measure that. And we do, and this is exactly what it looks like. Notice the queue depth goes up and down and up and down and up and down. But again, that analytics service is measuring trends. So I kind of draw a mean, I look at the standard deviation, and it's pretty much 1 to 2 from the norm. Fantastic. So those are a whole bunch of operational tests. But what about the overall structural integrity of my system, that bridge, those cracks in the pylon? Well, let's push aside the testing application for a minute. And let's actually take a look at a typical order entry kind of system. Now, these could be components, these could be services, but we're going to consider them components. So we've got order placement, we can adjust inventory, we email the customer, we can order more stock, and also we've got item pricing. All of these are involved. So let's see what happens. I place an order. Now, question. Is it my responsibility once that order is placed to decrement inventory? No, of course it's not. That's your responsibility. So I tell inventory management, decrement inventory. Is it my responsibility to email the customer to say your order's on its way? And when I say I mean order placement right here at the top. No, I tell email service or email component do that. Now, if the stock goes too low upon ordering, I need to order more stock. Is that my responsibility as order placement? No, that's yours, or supplier ordering. Order more stock. If the stock goes too low, we increase the unit price. I know, a little bad, but we do. So, is it my responsibility? No, I tell item pricing do that. Do you see any issues with the structure of my system right here? I sure do. Order placement is tightly coupled to the rest of the system, isn't it? That component or service is tightly coupled to everything else. Well, all of you probably have heard this. What are we supposed to always strive for? Loose coupling and tight cohesion. Create loosely coupled systems, we're told. Well, everybody always tells you to create loosely coupled systems, but no one tells you how to do it. Let me show you how to do it, because that component is too tightly coupled in the system. How to do it is something called the law of Demeter. Now, this is also known as the principle of least knowledge. The law of Demeter comes from the name of the goddess Demeter. Now, the goddess of Demeter was the goddess in Greek mythology of agriculture. She was responsible for producing all the grains in the entire world. But she had no idea what all of you did with them. So, the principle of least knowledge says a service or a component should have limited knowledge of other services or components. Well, of course. There's 3 rules within the law of Demeter. Rule number 1, don't talk to strangers. Rule number 2, only talk to your close friends. Rule number 3, only talk to those closely related to you. What does that sound like? Sounds like our parents when we were little kids. We go out to school and we go out to play. Don't talk to strangers. Only talk to your close friends. Yeah, well, let's see how to apply the law of Demeter. Little did we know, our parents knew all about this. They just didn't tell us. Okay, let's decouple the system. Is it my responsibility to order more stock? No. Are you ready? Should I even have the knowledge that more stock needs to be ordered? can I defer that knowledge that it needs to happen to somewhere else? And in fact, I can. I can defer it to inventory management. Do you notice something here? I have less knowledge about the system, hence less coupling. Is it my responsibility to increase the unit price? No. Should I even know that that needs to happen? Can I defer that to somebody else? Absolutely. I can defer that over to inventory management. Less coupling, less knowledge, hence less coupling. Now, notice, in this case, supplier ordering and item pricing are strangers. I don't know them. Inventory management and email are my close friends. Why? Can I defer that knowledge to anybody else? No, I kind of have to know that. There's nobody else I can defer that to. And that's the idea of creating loosely coupled systems. And we have. So, now that I've decoupled my system, how do I make sure that I maintain that structural integrity? And the answer? Fitness functions, tests. So let's write some. So these are tools we can write for structural integrity. And the first of these, let me show you 4, is something called ArcUnit for the Java platform, ArcUnit Net for the .NET platform, NetArcTest, also for the .NET platform, and SonarGraph, which works for a host of other kinds of platforms and languages, including JavaScript, as a matter of fact. So, how do we test this? How do we make sure that as we're applying changes to our system, that I'm not kind of recoupling everything together? Because entropy is a real thing. Let's write some tests. So here's an example in ArcUnit of how we can actually do this. Notice the name of the method here. Placement can only access notification. Classes that reside in a package placement should only access classes that reside in a package notification or inventory check. There we go. And this is a test that we can, in this case, hook up to JUnit or run in our CI/CD pipeline. Any sort of structural integrity, these are testing the architecture, not the functionality, the architecture itself. Here's another good example. Let's say we have a very traditional layered architecture. We don't want the presentation layer to access the database directly because we expect a lot of change and we want to kind of control change in the database. Well, so I write an architecture decision record to say only the business and services layer can talk to the database. Persistent can't. Ha! What do you think the first thing a UI developer is going to do? Oh, they're going to query the database directly because it's much faster. Yes. How do we govern these kind of structural integrity constraints? Fitness functions. And here is the test for it in ArcUnit, and then I'm going to show C#. Presentation layer cannot access persistence layer. No classes that reside in a package presentation should access classes that reside in a package persistence. And you know very well this will fail. I love the .because clause, because now I'm giving rationale and reason and justification for this integrity constraint. Because we have a closed layered architecture and we want to control change. That's why. I know it's faster, but change control is more important to us. This is the corresponding NetArcTest in C#. Types in the current domain that reside in the namespace presentation should not have a dependency on persistence. It's pretty cool. You know, these APIs and these tools are written in such a way that if you can verbalize your structural integrity constraint, the API matches it pretty quickly, or pretty closely. All right. Fantastic. So this is what it's meant to kind of test a software architecture. We can answer these three questions. Are changes that we're making impacting the overall architecture? Are changes to the environment impacting the architecture? We run unit tests all the time. But now we can run these unit tests against our architecture, the structure of that system as well. This happens all too often. By testing our architecture, both the structural integrity and the operational characteristics, you can actually avoid having this happen to you. Please test your architecture. Anyways, thank you all so much. Thank you. All right.